Thank you, George and Marek, for the introduction. We will now focusing on the first pilot sites, smart and automated operations. Together with me, I'm Max Friedemann from the Technical University 𝗏𝗏 𝗏𝗏, and they are research assistant. And together with me, they are sitting 𝗏𝗏𝗏 from Fraunhofer ICCS, Sohan from LTU, Luleå Technical University, then 𝗙𝗏𝗏𝗏 from the KGGHM, and Paul Schönherr from Technical University 𝗏𝗏 𝗏𝗏. We are focusing on 4 different technologies. They are provided together with us. And at first I will speak about the digital drill rig digitalization. But they don't change the slides. Yes. Yes, okay. First one, we will focus on the digitalization of drill operations together with the 3 technologies. Of course, the first one, sensor implementation and data acquisition. Second one, predictive maintenance. And the third one, material evaluation during drilling. The second technology is provided with the X-ray technologies for drill core analysis and smart sorting. Then an AI algorithms powered for metal ore processing and flotation will be explained, and last but not least, the digital smelter. Like you see at our agenda, 𝗏𝗏 focus all different mining sections and digitalization of these mining sections. So currently, at this speech of the first pilot sites, we will talk firstly about drilling and exploration, following about X-ray analysis of the drill cores, then flotation processes and smelting processes. Now I will start with the first technology, digitalization of drill operations. This pilot site is located at the Technical University 𝗏𝗏 𝗏𝗏 in Germany. We have a research education mine. It's an old silver mine, more than 300 years old, and we are doing still the research education for our students. We have still 5 levels accessible until to 220 meters and 19 kilometers of used drifts. What is the overall part of this project? So at first we equipped the 𝗏𝗏𝗏 𝗏𝗏, an exploration drill rig with a data acquisition system. We added sensors and a data logging system to this, and we doing real-time measurements and transmit this to our 𝗏𝗏 platform, our 𝗏𝗏 cloud. Of course, we evaluate this 𝗏𝗏𝗏 𝗏𝗏 in our mine. We do test drillings at well-known locations, and of course we do this at different situations, different drill bits, ore and host rock. What are the objectives of this? So the first one is to get a detailed status information to the operator. So currently at these normal machines, the operator has only 2 small manometers which will get the pressure of the hydraulic system, but they never know how deep they are drilling, how fast they are drilling, what is the rotation rate, and so on. Then we want to increase the efficiency of the drilling process. We want to get a faster learning curve for new operators. And then we have 3 different partners at our pilot site. They are developing algorithms with this data. The first one is to evaluate and analyze the rock being drilled, and of course analyze the wear of the drill bit in real time. For this one, we had different requirements. So we took a legacy machine, a 10-year-old machine, but you can buy this at this moment at the market. So the first one is we don't want to do any structural changes to the drill rig. We wanted a centralized digital data acquisition system with a live dashboard to the operator and of course a real-time dashboard. We want real-time data transmission to our partners and to the 𝗏𝗏 platform. So we need a very good infrastructure at our mine. And of course, we have in our mine very difficult environmental conditions. So we have nearly 100% condensing humidity and very acidic main water drains. Here you can see now different installations of the different sensors. You will see the displacement transducer at the left side of the machine, and this measures the position of the rotation head. And with this position, you can calculate the penetration rate and the borehole length. Here you see the 3 accelerometers. They are connected directly to the rotation unit and the gearbox. Here you see a sensor about the rotational speed. Overview the drill rod. And of this, of course, we overview also the hydraulic sensors, hydraulic circuit. We have 2 pressure sensors and of course a temperature sensor. And very important also is the flushing water. So we need to clean our borehole, and for this one we overview the flushing water with the flow meter and the pressure sensor. And on the right side of the picture you see our overall situation with the drilling rig, with the control unit and data cruising and dashboard for the drill operator. Now we are coming to data analysis. So in this picture you see two diagrams of one sector. You see one times the drill operator knows about the dashboard, what's actually drilling, and the other one we have our data to evaluate the drilling process afterwards and to get the efficiency, increase the efficiency of the drilling process. For this one, you see at the right side, the blue one is the penetration rate. It struggles a little bit, dependency on the host rock, on the rock situations we are drilling, and then you see the pressures, and of course the pressure you need to force down is increasing softly. And at the left side, you see the borehole length, which is always increasing. Now we are coming to our 2 main algorithms where I developed from our partners to the side. The first one is material evaluation during drilling, developed by Ølje Technical University, and they are using advanced tools for data filtering and normalization. And with this AI algorithms, the current drilling situation is evaluated and the boundaries between the ore vein and the host rock is identified. And at the right picture, you see such 4 boreholes and the model of these 4 boreholes. And the brown part, or yellow part, is more or less the ore, which is predicted with the algorithms, and the black and dark one is the host rock we are drilled. So from this one, you can very good evaluate which rock we are drilled while we are drilling. And the second one is to identify the rock quality. So identify the fractured zones in the borehole is important. And of course for this one, if you have a higher predicted fracture intensity, then you have a less competent rock. And of course we evaluated this algorithms to the drill cores. So we took our drill core, which we are from our mine, and had high fraction zones with high values of fracture intensity. We have mostly boundary conditions or mostly a very less competent rock in the mine. Next one is the predictive maintenance module. This is developed from our Greece partners ICCS, and it is implemented in the form as a machine learning, analytic tools, automated machine learning, and deep learning. And for this, it can predict the equipment degradation, especially for the drill bit. So with the prediction of the future health status and the drill bit, we can have a dashboard for the operator to show how many meters you can drill with the drill bit. And in the background, there's also a workflow automation engine from Frontier Innovations, which will trigger messages if some critical values of the degradation or some failures happened in the mine at the drilling process. So what are our advantages? We improved our core quality. So what we can say is that we have, with a more consistent penetration rate, we have longer individual core sections and we have fewer core breaks. Of course, the operator gets a detailed set of information and know how deep he is drilling, how fast he is drilling. And it's very important for new drillers and also for experienced drillers to know this section and to get a better status information about the drilling process. So what we can say is we approved the concept and took in legacy existing old machine drilling rig took this sensors and data acquisition system on it and integrated it in 𝗘𝗃𝗵 4.0. It is possible, and it's very important to increase your mine operations. Thank you very much for your attention. Now we are following with X-ray technologies for drill core analysis and smart sorting from Markus. Thank you very much.
Okay, so thank you, Max, for the introduction. My name is Markus 𝗏𝗏, and I will present 3 X-ray technologies for drill core analysis and smart sorting for smart and automated mining operations. So first I will start with drill core analysis. So at the moment the drill core analysis is focused mostly on lab assays, which are costly and time consuming, have long turnarounds, days, even weeks sometimes, which can slow down exploration decisions. And a faster and smart drill core analysis technology could accelerate the workflows there. So I will present 2 different technologies for drill core analysis, and that is X-ray computed tomography that provides volumetric 3D data and structural properties of the core, and the energy dispersive X-ray diffraction that provides mineral information directly on the spot. Okay, so let me start with the X-ray computed tomography. The X-ray computed tomography is a 3D visualization technique, and it reveals the internal structures of the object you are scanning. In this case, it's the drill core, and you don't have to cut it open. It is a non-destructive technology, and so the core can preserve for future analysis. It delivers the fully 3D information of the core, and with an automated image analysis, it opens very powerful insights into the drill core. However, there are some challenges and limitations, as it depends on the density and atomic number contrast. It is not always possible to differentiate the minerals that are similar in their properties. So we are talking more about mineral groups than individual minerals that can be visualized here. Yeah, so in this case we had a drill core from Freiberg, and we recognized 4 different mineral groups. So it was quartz and calcite forming one group, pyrite, chalcopyrite, and sphalerite as the second group, arsenopyrite, and galena. And on the right side you can see the images. So the black and white image is the raw X-ray computed tomography image. So this is just a 1D slice of a 3D data set. And then on the very far right side you can see the segmented image where the colors are showing the different mineral groups in the segmented image. Well, our workflow here was that we implemented a software tool that does the 3D data processing and segmentation. So the biggest challenge was to get started with the segmentation, and we developed a parameter-free segmentation tool, so that used the joint histogram method, so that we can get like a start value for an estimation of the segmentation of the mineral groups, and we could use that then to refine it and put it into our deep learning models to do the actual image segmentation into these mineral groups. The second drill core analysis tool is the energy dispersive X-ray diffraction. Compared to standard X-ray diffraction, it uses a fixed geometry, which makes it a lot more robust and even suitable for the application in the field, which is in contrast to the standard X-ray diffraction that allows that requires like lab conditions, very sensitive devices with like goniometers and things like that, which is something which you cannot use in the field. But the energy dispersive X-ray diffraction uses the fixed geometry to overcome that problem. It is also a non-destructive technique, and aside from basic cleaning of the samples, there's no further preparation needed. We scanned several cores from Freiburg at different positions, using the fixed angle geometry and the high usable flux. With the energy dispersive approach, we could reduce the scan time from 5 minutes to about 30 seconds. But there are also some challenges. We found out that we would need a site-specific calibration, and because of the orientation challenges, not all peaks that help to identify the actual minerals appear as expected. So there's still some work to do in this case. And now I will come to the smart sorting using dual energy X-ray transmission imaging. So in current state, well, many mines observe like declining ore grades, which demand a very efficient separation. And well, the sensor-based sorting can help in early waste rejection before crushing and milling, which can save the consumption of energy and water in the process, because there's less material that needs to be crushed and milled. So we are using the dual energy approach here, and so we are doing image analysis online on the conveyor belt using the dual energy X-ray, and we use deep learning approaches to identify different materials and separate the ore from the waste. So, but also there are some challenges here, but they are manageable. First thing is that we suspect that the model trained to one ore body may not generalize to other locations, and it is kind of time-consuming to produce the labeled data you need to train your AI models here, because like labeled mineralogical data is very hard to get and time-consuming to produce yourself. So this limits the training data sets for the AI models. We have also looked at the possibilities that the method provides, and we made up artificial multi-mineral samples to show the potential of the method. So how we can identify different minerals on the X-ray images, and you can see it on the picture here. From the left, there is like a standard photograph. In the center, there's the standard X-ray image, and on the right, there is the target minerals highlighted in green. But we did not just use these artificial a sample setup. We also got some sample material from the 𝗏𝗏𝗏 mine, and we applied our method here, and we could show a very good separation in the features that we could extract from the X-ray images to distinguish the ore and the waste. So that's all from my side, and we can move on to Wojciech, who's the next speaker.
Thank you, Markus. My name is 𝗏𝗏𝗏 𝗏𝗏𝗏. I represent 𝗘𝗃𝗃𝗏𝗏 and I would like to, in the next 10 minutes, introduce you to the AI-powered metal ore processing case. This case is implemented by the partners listed in the slide, and it's based on the real industry scenario as given by the processing plant located in Polkowice in Lower Silesia in Poland. This processing plant is operated by 𝗘𝗃𝗃𝗏𝗏, which is one of the biggest mining companies in the European Union. We produce about 30 million tons of silver and copper ore per year. And the case is related to the implementation of the AI methods into flotation process monitoring and operational control. In terms of 𝗫𝗏𝗈 project logic, we are in the second part of the value chain where 𝗫𝗏𝗈 is developing strategies for smart processing and smelter operations. Firstly, I would like to introduce a little bit flotation process as it is. So the flotation process is a mechanical separation of the materials based on the hydrophobic and hydrophilic properties of surfaces. And it takes place in the flotation cells of the flotation machines, where the pulp, which is the mixture of the water and the ore, is exposed to the compressed air. The bubbles of the air tends to stick to the hydrophobic surfaces, metal, and helps them to transport to the top layer of the machines when it's collected by the flotation froth. In the same time, the hydrophilic material, the waste rock, is transported to the bottom of the machine, where the separated stream of tail is generated. And in that way, we increase the copper content from the ore, where we have in 𝗘𝗃𝗃 about 1 to 2% of the copper, to the form of concentrate, which contains about 20% of the copper. However, the flotation might seem very simple. The industrial setup of flotation is very complex and should be considered as a multi-stage process. In the 𝗘𝗃𝗃𝗏, we can speak about 3 stages of flotation: rougher flotation, cleaning flotation, scavenger flotation, and also intermediate processes as reclassification and milling. This all process creates the loops of materials and creates the dependencies between flows, which creates a big challenge for process monitoring and control. To address this challenge, we propose the AI-powered copper ore processing tool, which is called the PIT system, photonic IT system. Its objective is to generally improve the mining process and mineral processing efficiency. We want to achieve the better selectivity of the process and achieve higher recovery rates of the valuable raw materials. And we want to focus on the efficiency in terms of higher material, water, energy, and better cost efficiency and flexibility of the process. And the main task, the main idea of the PIT system is to provide the very quick online estimation of the copper content in the flotation froth based on the AI algorithms. The PIT system is supposed to work in strong relation to the control room of the processing plant. It is composed of 3 main modules. The first module is the PIT visual system, which is installed directly over the flotation machine. The second module is a database that contains the froth images and all the parameters that are needed in the process. And the third module is the AI module, AI module responsible for the prediction and estimation of the copper content. So the basic, so the physical part of the system, the vision system, is basically the set of cameras, very specialized cameras, and the illumination system. It works over the flotation machine. In case of 𝗙𝗃𝗁, it is the rougher flotation machine, and provides the froth images to the database. Also, the database is also getting the flotation parameters from the SCADA systems and other parameters needed, for example, about the ambient temperature, humidity, and the pressure of the local conditions in the processing plant. Then, in this approach, the froth image is a key indicator of the flotation process. It brings the information about the process efficiency, process stability, and concentrate quality. And the task of the PIT system is to register the high-resolution images of the various types of the froth and analyze the features in the image and provide the information about the process efficiency. For the estimation of the copper is done by the AI. So, why did it disappear? Okay, perfect, thank you. Okay, so the estimation of the copper content in the froth is done by the AI. During the pilot sessions, during the MyAI project implementation, we generated the images, group of training images that were associated with the copper content that was tested in the laboratory. Then we took another image groups that were not associated, and we checked how different artificial neural networks estimate the copper content. And based on that, we select the best one that we achieved the average estimation relative error of about 6% compared to the traditional methods that are used in the processing plant based on the XRF methods. And with that knowledge, with that possibility, we opened the path for the flotation process optimization. Because we can get this information very quick, we can react very quickly in terms of machine control. We know already that the recovery, the function of recovery of in the process is a function, has the relation to the copper content in the froth. And then copper content in the froth is related to the flotation parameters. So by setting the flotation machine in the proper way, we can try to control the process, to work on this optimized parameters in terms of flotation time, recovery, and the CU content in the final concentrate. I know that that was very quick, brief information. For more, please check our website, project website. We are pilot site 2 in Poland. And also there is included a pilot demonstrator for online access. So you can check how the operation of the PIT system can look like for the in terms of operators application. And also the PIT system is described in many scientific articles created by the team. That's all from my side. Thank you very much. And I give the floor to Paul Schoenherr. Thank you.
Thank you very much. Ladies and gentlemen, I want to talk about our digital smelter, which is located also in Freiberg at pilot site 1.2 in the Institute of Non-Ferrous Metallurgy and Purist Materials. So first here you can see our top submerged lens digital smelter, which is one of the standard furnaces for smelting operations and converting operations in non-ferrous metallurgy. We have a pilot system one which is capable of was designed to handle very sulfur-rich concentrates and materials. So therefore we have a big off-gas cleaning unit which is part of the plant and taking up most of the space. So you can imagine that the top submerged lens smelter is a big hollow tube where you can insert your material and smelt it with a lens burner system, which also gets introduced inside of into the slag to have a higher volatilization of all the materials and a big reaction surface. Coming from the froth flotation process, we have copper concentrates going into our copper production process for raw copper production. So the copper concentrates needs to be handled with oxidative environments to produce some matte, and afterwards, after matte converting, we have a reduction process to produce some raw copper. This can be done, for example, in one of those furnaces, and very important is here the slag composition and of course the controlling of the temperature, our PO2 of the off-gas system or of the atmosphere, our flow rates of fuel, air, cooling water, off-gas composition, and also phase separation. Those are all very important data points and to drive those processes safely and with a high efficiency. So to address those points, we want to have the development of a digital assistant, a digital twin, with the help of a HSC chemistry software, which is connected or which is using chemical thermodynamics and also our process plant and advanced sensor data coming from a new PLC from Phoenix Contact. This is our old system containing of an old Siemens S200, which is not capable of performing those tasks in the newer ages of digitalization. So there, all the smelter got revamped. Also, old rotometers, for example, got exchanged to MFCs, which are capable of very precisely measure and measure the data, measure the flow of the oil and air and oxygen, which is needed to drive the plant safely. You can see an overview of the flow sheet, including the off-gas system in HSC. And here you can see, for example, the burner and the furnace part of the new PLC software overview, where the data also from the digital twin, which is coming back into the PLC, will be displayed. Here is also the overview of the off-gas treatment. To come to the advanced sensors, we are having all connected of the old sensors and the newer ones to our PLC. This includes also the digital in and outs of new sensors, which I come to in a second. Those data gets to be time aligned and gone into the HSC and also via OPC UA to our edge case, which is then connected to the minor node network or to other networks if necessary. We used, for example, the Harris electronite probe to detect PO2 inside of the slag and the copper, which is always also getting us a direct temperature measurement. This is not a continuous process, but a dip measurement, but a very important one to get the temperature of the melt and the PO2 to drive it safely and to know where we are in the process. Also, off-gas measurement is important, especially since we are handling sulfur-rich materials. We can determine in which state the process is if the sulfur is all extracted into the gaseous phase. So therefore, we can also be very precisely in our system, in our process. Coming to some also more advanced sensoric system acoustic measurements, which I come to in a minute. Here you can see our setup with a microphone in the top of the furnace and also the radar sensor for distance measurement and bath level height measurement. You can see the action for a short moment. You can hear the acoustics and the turbulence inside of the furnace. furnace and a very violent splashing of slags and metals. Coming to the bubble acoustic measurements for a moment, you can see here very nice like frequency spectrum spectrography, where we can extract the individual blobs of our system. This is very depending on viscosity and temperature and composition of the slag system, and therefore a very nice tool to determine if it's very fluent, if it's maybe starts to freeze in, then it stops bubbling because it's just blowing, not liquid anymore. Very dangerous also. This can lead to like enclosure of the melt and then with a sudden burst or a fuming, and this will be a very nice tool to safely drive and identify upfront those situations inside of a smelting and converting process. And you can also hear very nicely those things, which is driven by very experienced smelting operators. They hear everything in one ear, and when something's happening, they know exactly, okay, I need to do something. But this needs to be a little bit more automated to have a more secure way to drive those smelters. Here you can see also the lens removal. It suddenly reduces also the bubble intensity because there's no bubbling anymore. So you can here also see if something's happening which is not planned, or you can verify that, for example, lens position is probably driven. Coming to our new SPS or PLC, sorry, SPS is German. We can now measure melt bath level, bath movements, turbulence, bubble formation. Also, this is highly dependent, so it's very individual for each process and for each material system. So there is a more of a generalized process involved here, or more generalized information. With a high amount of campaigns and data, you can also train AI systems with those informations, but this needs very individual training and campaigns. Oxygen partial pressure is very helpful for state of the process, temperature directly in the melt as well, off-gas composition for safety and process parts, and digital furnace control system and mass flow control meters to round everything up and have a procedure digitized and automated. Those smart process simulation will then help the metallurgists to supervise those metallurgical processes and will lead to safer and more efficient process. Coming to the KPIs, the production performance will increase because we know where we are in the process way better. We can improve impurity removal and metal recovery, as well as energy consumption savings, because we can also reduce process times and specify the windows in which the process is completed to go on into the next steps. As well as, of course, reduction in resource consumption. When we know where we are in the system better, then we also can adjust fluxing with less flux, for example, or going lower in temperature, which saves energy in quite huge amounts. That's from my side. I thank you very much for your attention, and we are open for questions. After the questions, I think we have a short coffee break.
Are there any questions? Yeah, okay, I see.
So thank everybody for the interesting presentations. I have a question on the tomography and the analytics. So for me, I'm also part of the smelter team. So I think what can these techniques do for us in smelting? So my question would be, if I have a slag phase, which is not homogeneous, you will have a different type of phases forming, like spinels, or I may have also metal droplets of non-separated metal or matte, which is a sulfidic phase. So maybe several phases inside a piece of slag, and then could you conceive of analyzing with your techniques, not only tomography, but also the other techniques that you apply to the drill cores, and inform us about how much metal are we losing because we are operating in such a way, what types of phases are formed in my solidified slag? Do you see it applied transferred also to our domain, let's say?
Well, in general, I think yes, but it strongly depends on the size of the object you're looking at. So if you're looking at a piece that is a few centimeters in diameter, yes, that's absolutely possible. But if you're talking about like 30, 50 centimeters or meter, you will not be able to penetrate it with the X-rays, so you will not be able to generate an image at all. So it really depends on the size. But for smaller objects, up to a few centimeters, it should be possible.
So potentially in fragments of slags, or if we go to the university settings where we do crucible experiments, then potentially, which are small by nature, at least they're in the centimeter area, potentially you can give us another view on the analytics that we use in our research. So we would like to talk about this later on. It's super interesting for us.
Yes, sure. Sure, we can do that.
Thank you.
Okay, are there any other questions? Yeah, okay, here up front.
Thanks for the interesting, all of the presenters. Quite interesting technologies. This question goes more to the applicability of this, and especially the computed tomography and X-ray scattering analysis for drill cores. Usually, I know your technology is meant to be used also on the field, right? So how does it affect the local conditions? Let's say on the rig side, it's high temperature, high humidity, the environment, or it's very cold settings, let's say drilling in the Arctic. Does this affect the results, your experience?
You need, well, you can use those devices on the field, but you need to provide some kind of environment for it to operate. So, but that depends on your climate. But it would be possible, for example, to put that into a van, like in a small truck, where you can put the device and you can keep the temperature inside that to like a level, let's say above freezing and below 40 degrees or something like that. So that would be suitable. Yeah.
Thanks.
Any more questions from the audience? Then I have still one more quick one. My question will be to Max. You showcase some inputs about the economical aspects of the digitalized drill rig. What about the environmental aspects? Can you elaborate more on that?
If you talk about environmental aspects, we overview the drilling process, and of course we need a lot of water for example, flushing water examples. So if we can have a look to the data and see the flushing water pressure is too high, we have too much flow through this, we can reduce it and reduce water consumption overall the drilling process. This is one example what we can do with the data. Of course, there will be some other points that we maybe reduce some energy consumption to optimize the drilling process, that we don't pressure so hard against the rock, but sometimes it's smarter or more efficiently if you drill more which is slower, without pressure, without less energy consumption, and then you have an efficient drilling process that you have a very small drill bit degradation and so on. So if different conditions, we can focus on environmental conditions to reduce the environmental impact.
Thank you very much. Thank you again for all the speakers. We will adjourn for a short coffee break and we'll come back